Every day, we're surrounded by an invisible energy that our bodies can only detect a tiny part of. An important example of it is the light you see using your eyes. However, we still use the energies our bodies can't detect all the time in our daily lives. This video serves as a brief introduction to electromagnetic waves. I'll be covering what electromagnetic or EM waves are, the electromagnetic spectrum, and properties of electromagnetic waves, along with some basic calculations you'll need to understand. As I said earlier, we're surrounded by EM waves. We use them for communication, for heating our food up, to see in the dark. There's something we've learned to harness for our own uses. Watching this video is actually an example of you using EM waves. EM waves themselves are a category of waves that all travel at the same speed in a vacuum. By vacuum, I mean somewhere where there is no matter, like in space. They're an example of a transverse wave, which I'll come onto in a second, and are made up of an oscillating electric field and magnetic field. A big thing with these waves is, unlike sound waves, they don't transfer matter. They don't need a medium to travel through. Sound needs to vibrate particles, such as those in air, in order to transfer energy. EM waves can propagate without them. And talking of energy, the energy EM waves transfer depends on their wavelength. To help you understand all that, here's a quick overview of transverse waves. If you haven't seen one already, this is what a transverse wave looks like. The wave oscillates perpendicular to the direction of energy transfer. Here, I've picked a point on the wave, and as you can see, that point only moves up and down, yet the wave is able to transfer energy towards the right. If I stop the wave for a second, we can determine the wavelength of a transverse wave by measuring the distance between two peaks, or measuring the distance between a full trough and a full peak, or measuring the distance between two troughs. A trough is just a dip in the wave. The amplitude is simply the distance between the centre line to the highest point of the wave, or from the centre to the lowest point of the wave. And finally, the frequency in hertz of the wave is the number of times a full wave cycle passes a certain point in 1 second. For the wave you're seeing on screen right now, the frequency is about 1 hertz, or 1 cycle per second. All of this information is important, and you should be able to recall it outside of the electromagnetism topic. Going back to the realm of our invisible energy, I said earlier that the energy of EM waves depends on their wavelength, so also their frequency. The EM spectrum goes all the way from radio waves to gamma rays with increasing frequency and decreasing wavelength. The wavelength of the largest radio waves is comparable to the size of a tall building, and the smallest wavelength of gamma rays is comparable to the size of atomic nuclei. Visible light ends up being slap bang in the centre of this spectrum, and also has its own spectrum. Visible light is made up of all of these colours, and they too have their own wavelengths and frequencies. For now, it's sufficient to just know what waves make up the electromagnetic spectrum, and what happens to their frequency and wavelength as you move up and down the spectrum. Also bear in mind that it's a continuous spectra. For example, the smallest radio waves are approaching the size of the largest microwaves, and their differences get very hazy. In essence, they're all the same type of wave. They're EM waves. We've just given names to different sections of wavelengths and frequencies. To help you remember all of these waves and the order they come in, so gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves, I use the mnemonic Grandma's Xbox uses volts in my room, going from the highest frequency and shortest wavelength to the lowest frequency and highest wavelength. You may very well find some other mnemonics to use, but remember that they may have a different order than this one. An important aspect of EM waves that ties them all together is that they all travel at the speed of light, 300 million meters per second in a vacuum. I've got that written in standard form here, and I'll be using that more and more, so make sure you're comfortable with that notation. Using this information, we can determine the wavelength or frequency of the waves with this equation. V equals F multiplied by lambda, where V is the wave speed in meters per second, F is the frequency in hertz, and lambda is the wavelength in meters. You need to be comfortable rearranging this. So if you prefer to rearrange your formula using the formula triangle, I've got that on the right for you. Here's a quick example of a very basic question you could be asked. Red light has a wavelength of 680 nanometers. At what frequency will it travel at in space? So we know that the wave speed is 300 million meters per second, or 3 multiplied by 10 to the 8 meters per second. We know that lambda is 680 nanometers. That's the same as saying 680 times 10 to the 9 meters. We're looking for what f is. We can rearrange our formula to give us f is equal to v over lambda. So that's just 3 times 10 to the 8 over 680 times 10 to the 8. And that gives us an answer of 4.4 times 10 to the 8 hertz. So for red light travelling in space, 440 million wave cycles pass a certain point every second. Finally, I'd like to emphasise that the energy of EM waves increases as their frequency increases, and thus their wavelength decreases. If you imagine each wave cycle as a packet of energy, the one with the higher frequency will be transferring more packets in a second, so it's got a higher energy. The wave below on the right is more energetic than the wave on the left. I hope that helped explain some concepts about electromagnetic waves. In the coming videos on this topic, I'll be diving deeper into each of the different waves in the EM spectrum, including their properties and uses.